In this video, we're going to cover section 4.5, graphs of sine and cosine functions. Now, we've graphed sine and cosine functions from the unit circle previously, so this video is going to pick up with the section after that. So here are a few cycles of the sine function. So one cycle is when it starts at the what I'll call the equilibrium line, and it goes up, down to its lowest point and back to the equilibrium line. So notice it hits that equilibrium line 3 times. In this case, the equilibrium line is the x-axis, but not always after it goes through some transformations. And then the highest and lowest points, this is the amplitude, and this is where we get the range from. Here, a period length is 2 pi. So again, we have 3 cycles in this sine function. The domain is negative infinity to infinity, so please remember this is sine of, I'm going to call it sine of theta. We can put any angle we want to, and we find those angles by going through the unit circle. We can go around the unit circle multiple times. And that theta here is written as the x value. So this x is the theta, the angle that we put into the sine function. And this is the output, which is the sine of x. The range is negative 1 to 1. We can only get those values until we have transformations. The period is 2 pi. It repeats in every interval of length 2 pi, because again, after we go around the unit circle once at 2 pi, we go through the same process every length of 2 pi. Now this is also an odd function, so sine of negative x equals negative sine of x. Meaning, if I took this sine function, and let's try to rotate that about the origin. Let's see, I'm going to have to rotate and shift. So there is symmetry around the origin. I don't know if that showed up very well, but it's symmetrical about the origin. So now let's look at the graphing variations of y equals sine of x. So they've got 5 steps here, and the key will be just to go through these steps multiple times. And we're going to do it a little bit at a time. So this first one, notice, our only transformation is the 1/2. That's going to change the amplitude. So one of the steps is to identify the amplitude and period, and I'll show you how to do that. And then we find the values of x for the 5 key points. Those are the 3 x-intercepts, which are what I call equilibrium points. That's on that line that it comes back to, the maximum point and the minimum point. Okay. Now, we'll talk about how that's done when we see some examples of that. We find the values of y for the 5 key points, connect the 5 key points with a smooth curve, and graph one complete cycle, and then extend to the right or left as desired. So we're going to determine the amplitude of y equals 1/2 sine of x. So this is a multiplying outside, so this is a vertical stretch or compress. So instead of going up to 1 and negative 1, we go half as far. So my 5 key points here will be 0, pi halves, pi, 3 pi halves, and 2 pi. That's what it means when it says find the 5 key points. Now, if there's no shift horizontally, if there's nothing inside, those will always be our 5 key points. And then we graph the points. So we've got 0, 1/2 instead of going all the way up to 1, back to our equilibrium line, down to our amplitude, negative amplitude, and then we connect this with a curve. Your curves don't have to be great, but I do not want to see straight lines. We need to know that it is a smooth curve. So that's example 1. So now let's look at how to find the amplitude and period. So the graph of y equals a sine of bx, where b is greater than 0, has an amplitude of the absolute value of a and the period of 2 pi over b. Okay, so the amplitude is the distance from the equilibrium line down to the lowest or the highest point. and the period is 2 pi divided by b. So again, when we had sine of 1x, our period was 2 pi divided by 1, just the 2 pi. And on the previous problem, when we had a 1/2, the absolute value of that became our amplitude. Notice if you had a negative 1/2, that would reflect it across the x-axis, and you would be going down instead of going up when you start at the origin. So let's graph. Let's determine the amplitude and period of y equals 3 sine of 2x, then graph the function. Now notice I don't have my 5 points because maybe this isn't 2 pi. If my period changes, then I'm no longer have a period of 2 pi. So the amplitude equals the absolute value of 3, so that's just 3, and the period equals 2 pi divided by b, which is our number multiplying our x inside, so that's just pi. Now there's no shift, so I go from 0 to pi. Now this is where, if you are comfortable with fractions, that's going to make it a little bit easier. Half of pi will be this point, so that's pi halves. And then we take half of that again, so half of pi halves is pi fourths. Then, two things, you can either add these two or multiply by 3 to get 3 pi fourths. Now, 1/4, 1/2, 3/4, that one's not too difficult, but we'll get some other, let me erase the right things here. We'll get some other values that might be a little bit more tricky. So here are our 5 key points. Now, there's no reflection, so I know that it's going to be going up and down. My amplitude is 3, so I'm going to be going up to +3, down to -3. I'm going to put those values here, and then I connect it with a smooth curve. Now, the graph of y equals a sine of bx minus c. So here we've got a bx minus c. We already know what to do with b. Period's the same, amplitude's the same. But here we have a phase shift. So this is shifting to the left or to the right. And to get the phase shift, we take c over b. And again, this is, if it's positive, it shifts to the right. If it's negative, it shifts to the left. But please note that they're not taking the negative c, they're taking this value c. What I would like you to remember is it's the same as any other transformation. If I had the square root of x minus 5, you would know, oh, that goes right 5, because it's the opposite of what we would think with that negative sign. That's the same thing here. If there's a subtraction sign in here, and we don't have a subtract -3, so simplify that out if there is. If it's a subtraction, it moves to the right. If it's a addition, you move to the left. So we're going to go through example 4. This is putting most of these things together now. We're going to find the amplitude, and that's the absolute value of 4. We're going to find the period, so that's 2 pi divided by b. Our b is 2, so that equals pi. And then we're going to find our phase shift, and the phase shift is found by doing c over b, and so that would be 2 pi thirds divided by 2. So let's rewrite this. 2 pi thirds times 1 over 2. Well, that means my 2's are going to cancel out, so my phase shift is pi thirds. Now, there's a couple ways to do this. You can reason this out however you would like. I'm going to share with you what I have found works for a majority of the students for a majority of the problems. Okay, some don't need this much, but the key, we're still working on finding our 5 key points. We have a period change and a phase shift change. What I do is I take the period, and if I say if there was no change on the period, on the phase shift, I mean, what would my values be? And I'd have 0, pi fourths, pi halves, 3 pi fourths, and pi. And then to that, I'm going to add pi thirds to each of these to get my new 5 key points. So 5 key points. This is going to be pi thirds, pi fourths, plus pi thirds. You can use a calculator to assist you if you need with these fractions. That's going to be 7 pi twelfths. Pi halves plus pi thirds is 5 pi sixths. 3 pi fourths plus pi thirds is 13 pi twelfths. And pi plus pi thirds is going to be 4 pi thirds. So these are my new 5 key points after the phase shift. Again, this is what they would have been with a period of pi and no phase shift, so I need to add that phase shift to each of those to give me the 5 key points. Now, I am not going to be super picky about the spacing here. I just want them labeled, so I'm going to do pi thirds, 7 pi twelfths, 5 pi sixths, 13 pi twelfths, and 4 pi thirds. They should generally be evenly spaced, but they might not match the pi third spacing at the beginning, and that's okay. Now there was no negative sign, so I'm going to start at 0, and then at 7 pi twelfths I'm going to go all the way up the amplitude, back to the equilibrium, down to the negative amplitude, and to the equilibrium again. And there is my sine curve, or my function of 4 sine of 2x minus 2 pi thirds. Now cosine we've already graphed again from the unit circle. This gives you another diagram of that. Difference between sine and cosine is sine starts at the origin and moves up, cosine starts at 1 and moves down. But again, it's just a shift. If I took this part of the cosine graph and then slid it over, that would be the sine graph. Okay, so it's just a translation, again from the cofunction properties. Pretty much everything else stays the same. Like the processes we just discussed will stay the same. So amplitude and period, we're going to solve by finding the same way. So here our amplitude will be the absolute value of -3, so that's 3. And then we have a period of 2 pi divided by pi halves. So let's find that period. That's 2 pi times 2 over pi. These pi's cancel, and the period is actually 4. So in this period, we do not have pi's in our graph. So here's 4. So my 5 key numbers will be 0, 1, 2, and 3. My amplitude is 3. And again, since we're dealing with a cosine function, we have to reflect across the x-axis. So instead of starting at the top of the amplitude, we start at the negative amplitude, go to the equilibrium line, go to the positive amplitude, back to the equilibrium line, and then down to the negative amplitude. And again, we want a smooth curve, something like that. And there's our graph of -3 cosine of pi halves x. Now we do this the same way to find a phase shift, C over B. So again, this part right here, star this, that is how we graph a sine or cosine function, how you find the amplitude, period, and phase shift. So let's do example 6. The amplitude will be the absolute value of 1/2. So we're only going up to 1/2 and down to negative 1/2. Again, we're graphing a cosine function. The period equals 2 pi divided by b, the number that is multiplying by x. So we have 2 pi over 4. That is pi halves. And the phase shift is our c over b. So that's pi force. Now it's a plus, so we're going to go to the left. We're going to go left, pi force. Now, with a pi halves period, I'm going to look at the original points that I would normally have, 0, and then I've got 3 points in the middle, then pi halves. So if there's no phase shift, I would be going from 0 to pi halves. So pi force would be here, half of that would be pi eighths, and then we triple that to get 3 pi eighths. Now to all of this, I need to add, since I'm going to the left, I need to subtract pi force. So this is going to give me negative pi force is 1, and then negative pi eighths. These weren't negative signs, those were just markers. So negative pi eighths, 0, pi eighths, and pi force. So that's what all of these new places, these new key points become. So I've got negative pi force, negative pi eighths, 0, pi eighths, and pi force. Those are my values. I already have the max, the amplitude, and so the cosine function is going to start negative pi force down to, let me change color. Start here, negative pi force 1/2, then the equilibrium line, then the negative 1/2, equilibrium line, and then back up to the positive amplitude. And we get a cosine graph that looks something like that. So now let's look at vertical shifts of sinusoidal graphs. This is just an adjective meaning of or like the sine function. So we've got this type of thing. This plus d is going to be the vertical shift. And this is going to be like we would expect. If it's positive, we shift up. If it's negative, we shift down. And so everything else is the same. Just when we do the amplitude, we've got to take into consideration the shift. So take that shift plus the amplitude. The minimum value is d minus the amplitude. And that's why I like to think of the equilibrium line. So when I have a minus 1, my equilibrium line goes from the x-axis down to negative 1. Okay? So here, I'm going to make negative 1. This is my equilibrium line. So if I'm graphing 1/2 of cosine of x minus 1, my amplitude is the absolute value of 1/2. That means I'm going to go up to negative 1/2 and down to negative 3/2. Cosine of x, nothing else changes, no vertical shift, no change of the period. So I've got my 0, my 2 pi, pi, pi halves, and 3 pi halves. So I start up, let's change graphs. Color, I've got, because it's a cosine, I start up at the positive amplitude, meaning 1/2 above the equilibrium line. Then the equilibrium line, the negative amplitude, equilibrium line, the positive amplitude. And there is my graph of the 1/2 cosine of x minus 1 using that vertical shift. So example 9, modeling a tidal cycle. Figure 4.79 shows that the depth of water at a boat dock varies with the tides. The depth is 5 feet at low tide and 13 feet at high tide. So that just means here's a dock and here's 5 feet at low tide and 13 feet at high tide. On a certain day, low tide occurs at 4 a.m. and high tide at 10 a.m. So if y represents the depth of water in feet x hours after midnight, use a sine function of the form a sine of bx minus c plus d to model the water's depth. So we have a scenario here that we need to model. To assist this, let's do a couple things first. Let's look at the equilibrium line. We have the high and low tide, so the equilibrium line is going to be in the middle, and so that's 9 feet. That also means that here in the middle, so 4 a.m. to 10 a.m., that's 6 hours, so at 7 a.m., it's going to be at that 9 feet mark. And then again at 1 p.m., 3 hours later, it'll be at the equilibrium line again. And then at 4 p.m., we'll see it at low tide. So it kind of looks like this. Okay, we were asked to use a sine function, and so we're going to take this and we're going to shift it from 0 all the way to 7. Remember, sine starts at equilibrium, and so we're taking that first equilibrium point, and that's going to be our phase shift. So phase shift equals 7. We've also got our period. Well, period from 7 to 1, that is 6 hours. So our period is 12 hours. Our amplitude, I'm just writing all this information down. We're going to use it in just a second. Our amplitude is 4 hours because we have, 4 feet. We have 4 feet above the equilibrium line and 4 feet below. And then, so we have phase shift, period, amplitude. Oh yes, a vertical shift of 9 feet because the equilibrium line went from the x-axis all the way up to 9 feet. So there are a few things we could throw in our equation right now. Y equals our amplitude times sine of some things we don't know yet plus 9. So to start figuring out what our B and our C is, let's look at the period, because the period equals 2 pi divided by B, the number multiplying by x. I can swap those spots, the 12 and the B, so B equals 2 pi over 12 or pi 6. So I know I have pi 6 times x. Now the phase shift, 7, equals C divided by B, which is pi 6. So I'm going to multiply both sides by pi 6. That will cancel these out on the right side. So C is 7 pi 6. Now I put in a negative because I shifted to the right. I could have come up with an equivalent equation by shifting this to the left a little bit as well. But there is our equation. So that's how we can find this equation from looking at a graph, period, amplitude, vertical stretch, phase shift, all of those things, and working backwards. That finishes our notes for section 4.5. Thank you for watching.